Okay, so what we're going to cover now are exponents and polynomials. Okay. First, I need to make an assumption, just like we've done in the past. I need to start off with an assumption, and our assumption is assume we have x to the n where n is greater than 0. We are going to call x our base. We're going to call n our exponent. Okay? With a and b an element, that does need to be an element of n. Okay, now again, mathematical notation. That right there, a weird looking E, it's really just a sideways U with a line in it. Okay, that stands for element of. Okay, so in other words, what we have is we have a variable x, we have an exponent n. Okay, now later on you're going to see where a and b come in, but we're going to assume that a and b's are elements of all exponents. Okay, and that's what that phrase means. A and b are elements of n, and that therefore a and b lie in the set of n. Okay, now another thing I want to make you aware of. We have x here. Earlier we were working with A, B, and C. We call A, B, and C constants. Okay? In other words, they're just numbers, and they're fixed numbers. They take A, B, and C take on a specific value. This A and B, they take on a specific value. They're just a lowercase a and b, which are elements of exponents. Okay, so these the A, B's, and C's that we were working with before in previous videos, we call those constants. In other words, they're just numbers. They're fixed numbers. They're already given a designated value. However, x we call a variable. And that means x can take on whatever number it wants to take on. In other words, you use x in a notational form that unless you establish x as taking on a specific value, it remains x. Okay? It is a variable. In other words, unless you specifically label x as taking on a specific value, it is not a constant. It is not a given number. It can take on any number. Okay? Any real number can be x. Meaning that all operations you use to define how x is going to be used in an equation or something must allow for the fact that x is a variable and it can take on any value unless you constrain it further by giving it a specific value or by only letting it take on specific values. Okay, this will become clear as we get into later videos, and it'll even become clear in this video as well, exactly the difference between x and the constants. Now, moving forward, let me get my blank paper out here. Okay, first what we're going to do with regard to exponents in particular, not polynomials yet, but what we're going to do with exponents in particular is we're going to lay out some rules. So I'm going to write these rules down. I want you to also write them down and familiarize yourself with them. Okay, so these are Rules of exponents. What are the rules of exponents? Well, x to the a times x to the b equals x to the a plus b. Now, let me just say something real here. You know, referring back to the discussion I just had about x being a variable and a and b being constants. The way we would look at this, if because a and b are constants, they take on a specific value, they take on a specific number, meaning that if I let a equal 3 and b equal 4, okay, then what we have here is x to the third power times x to the fourth power equals x to the 3 plus 4 power, which equals x to the power of 7, okay? But you notice how x stays in an operational format. We do not place a specific value to x because x is a variable, but we do place specific values to the constant term, okay? We can do that right off the bat. Again, unless we constrain x to be precisely some value or some range of values, you keep x in its operational format. In other words, it is a variable and it stays a variable. Moving forward in the rules of exponents. Okay, so x to the a divided by x to the b equals x to the a minus b. X to the a, I know my a's look like 9s, but you know, just get over it. X to the a to the b equals x to the a times b. X, y, y just being another variable, okay? X, y to the a equals x to the a, y to the a, okay? X divided by y to the a equals x to the a divided by y to the a. In other words, a can just be distributed in multiplication and division, but if x and y are two different variables, okay, two different variables, then you cannot combine, you know, you can't sort of say x times y to the a. This is x times y to the a, but you can't say, for instance, x times y to the a. That is not the same as that, because because y is a different variable. This is saying that x has an exponent of 1, y has an exponent of a, and that is not obviously the same as this. Moving on, we have 1 over x to the a equals x to the negative a. The square, or excuse me, the a root, the 8th root, not the number 8, but the ATH, 8th root of x equals x to the 1 over a. The 8th root of x to the b equals x to the b over a. Okay, so you see how the root goes in the denominator of the fractional exponent. X to the 1 equals x, x to the 0 equals 1. Now, y'all should be familiar with exponents from grade school. That said, you know, most of this stuff is most of these operations you've seen before, and we're actually in a minute here going to apply actual numbers to some examples, and put in some actual numbers for A and B, and work out some examples. You know, you've seen that x to the 1 equals x. I'm sure you've seen that before, and that's just simply saying, so I'll place a specific value to x. So 3 to the first power equals 3, okay? Why does x to the 0 equal 1? So in other words, if I have 3 to the 0, that equals 1? Does that make any sense whatsoever? Let's prove this. Okay, let's prove that. The rest of these don't really need proofs, but let's prove this. Okay, so why is x to the 0 equal 1? Well, here you go. X to the 0, okay, can be rewritten as x to the 1 minus 1. Okay, now if we move back up here to that rule right there, this also can be rewritten as x to the 1 divided by x to the 1. And guess what? That equals 1. So 3 to the 0 equals 3 to the 1 minus 1, which can be rewritten as 3 to the 1 over 3 to the 1, which can be rewritten as 3 over 3, which equals 1. Okay, so that's a proof of x to the 0 equals 1. We are missing one critical thing here, especially in terms of these fractional exponents. Okay, if this is the case, if this is true, I shouldn't have moved that. If this is true, okay, then what is 0 to the 0, right? What if x takes on 0? Because remember, x is a real number and 0 is a real number, right? So what if we have 0 to the 0? Well, if we use this logic here, then guess what? At some point, we're going to have 0 over 0. Okay, and that means that 0 to the 0 by definition is undefined. Okay, because again, because you can't divide by 0, right? And at some point, using this rationale, we would have to be able to rewrite 0 to the 0 as 0 over 0. And that's defined. That's undefined. That's unsolvable. So it's interesting how we can take these exponents and kind of back out the logic behind mathematics, because remember, mathematics is sort of the purest form of communication, and is certainly the purest form of communication. The most used form of communication in economics is mathematics.